Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to determine the amount of ions you have in solution after a certain reaction has occurred. So let's get into this. So in this problem we have a 300 milliliter sample of a 0.100 molar barium nitrate solution, and that is mixed with 100 milliliters of a 0.300 molar sodium phosphate solution and a white precipitate results. So they give us three questions. One, what is the identity and mass of the white precipitate? Let's begin with that one. Okay, so to find the identity and mass of the white precipitate, we need to first have a balanced equation. So we're going to have to take the barium nitrate and the sodium phosphate and write out a balanced equation for that. So let's go ahead and do that. So we have barium nitrate. So barium nitrate, the formula is going to be BaNO32 because barium has a 2 plus charge and your nitrate ion has a 1 minus charge, so you need two of these to balance the charge. So that's the formula for barium nitrate. That is going to be aqueous plus we have the sodium phosphate. So we're going to have Na3PO4, and that's going to be aqueous too because these are solutions. And again, the sodium ion is a +1 charge. Your phosphate ion has a 3 minus charge. So you need 3 sodiums to balance the charge in your phosphate. So this is the formula for sodium phosphate. And then we need the products. So once you have these, you realize that this is going to be a double displacement reaction because you have two compounds as your reactants, and they're both ionic compounds. So that is a dead giveaway that you have a double displacement reaction. And so the outside ions are going to come together to form a product. So we have the phosphate ion has a -3 charge. We have the barium ion has a +2 charge. So we're going to have the balance of charge there. And when you do that, you're going to get Ba3PO4 2. And then we have our other compound, and then we're going to bring the inside ions together. So sodium and nitrate are going to come together. Sodium has a +1, nitrate has a -1. So they're 1 each to balance a charge. So that's going to be sodium NaNO3. Okay, so we're told we have a precipitate. So we need to figure out which one of these forms a solid. So you need to know your solubility rules. So right away, one of the first rules that you know from your solubility rules is that all nitrates are soluble, all group 1 metals are soluble. So this is soluble. That's going to be aqueous. So by the process of elimination, the only thing left is the barium phosphate. And if you look at your solubility rules, you'll see that phosphates are generally insoluble. There are some exceptions. So this is going to be your solid. So we've identified the solid as barium phosphate. And so that's the first part of question A, the identity. Now we have to figure out the mass of the precipitate. So we need to figure out the mass of our barium phosphate. And in order to do that, you have to recognize that this is a limiting reagent problem. How do I know that's a limiting reagent problem? Well, the dead giveaway is that they give you the amounts of both reactants. So for the barium nitrate, they give you 300 mils of a 0.100 molar solution, right? So they're giving you a certain amount of the barium nitrate, and they give you 100 milliliters of the 0.300 molar solution. So they're giving you an amount of sodium phosphate, and they're saying, hey, they react together. We're mixing these together. They don't give us any other information. We don't know which one is going to run out first, which would be the limiting reagent. So we have to figure that out first. So one of the ways you could do that is the limiting reagent is going to limit the amount of product formed. So if you take each amount of your reactant and you do stoichiometry and you calculate how much of the barium phosphate is produced from each of these, then you look at, well, which one gives me the lesser amount? The one that gives you the lesser amount is the limiting reagent. It limits how much you can make. Okay, so that's the way I'm going to do it. So I'm going to take the barium nitrate first. So I have 300 mils of barium nitrate. So I'm going to take the 300 milliliters of BaNO3/2. And I'm going to start to convert. So I need to get to barium phosphate. So anytime you are going from one substance to another, you have to use the mole ratio. So in this case, we're going to get the mole ratio from our balanced equation. And so we need to make sure this is balanced. So here I have 1 barium. Here I have 3 bariums. So I need a 3 over there. Okay, so the bariums are balanced. Now for the sodium, so I have 3 sodiums here. I only have 1 here, so I'm going to need a 3 over here. Okay, so now for the nitrates, so I have 2 nitrates over here, and I have 3 nitrates over here. So I'll have to figure that out. Oh wait, no, I'm sorry. I forgot to multiply by the 3 coefficient. So here I have 3 times 2 is 6. So I have 6 nitrates over here. And here I have 3 nitrates. So I'm going to have to change this to a 6. Okay. Now I have the balanced nitrates, but look, my sodiums are now unbalanced. I have 6 over here. I only have 3 over here. So I'm going to have to put a 2 here to balance. So now 2 times 3 is 6. So now my sodiums are balanced. Okay, so nitrates are balanced. My barium is still balanced. My sodiums are balanced. What about phosphate? Lastly, phosphate. So I have 2 phosphates, and over here I have 2 phosphates. So it's all balanced. Now that I have a balanced equation, I can go ahead and use stoichiometry. So in stoichiometry, if I'm going to use a mole ratio, I got to get to moles. That's the first step in a stoichiometry problem. You got to convert your unit that you're given to moles so you can use the mole ratio. So I have milliliters here. They give me the molarity. So if I could get molarity, I can use that as conversion factor. Molarity is moles over liters. So if I can convert this to liters, I can use that to convert liters to moles. So I'm going to use my first step. My first conversion is going to be 1 milliliter of the BaNO3/2, and this is a solution, right? We're talking about a solution. And so that's going to be equal to 1/1000th or 10 to the negative 3 liters of the barium nitrate solution. Okay, so then the milliliters of the barium nitrate solution cancel out. Now I have liters. So now that I have liters, I can use the molarity as a conversion factor. So this tells me that for every 1 liter of barium nitrate solution, I have 0.100 moles of that solution. So since I have liters on the top here, I'm going to put liters on the bottom. So 1 liter of barium nitrate solution is going to give me 0.100 moles of barium nitrate. Oops. So liters of the barium nitrate solution cancel out. Now I have moles of barium nitrate. So now I can use the mole ratio between barium nitrate and barium phosphate. So you can see here that for every 3 moles of barium nitrate, I get 1 mole of the barium phosphate. So I'm going to go ahead and use that mole ratio. So since I have moles of barium nitrate on top, I'm going to put 3 moles of the barium nitrate on the bottom. And I'm going to put 1 mole of barium phosphate on top. So moles of the barium nitrate will cancel out. Now I have moles of the barium phosphate. And now I'm going to convert that to grams using the molar mass of barium phosphate. And then I'll get the gram amount. Since they're asking me in A, what is the mass of the white precipitate? I'm going to convert that to grams. And I calculate the molar mass. And when I do that, I get 601.93. So 601.93 grams of the barium nitrate, or barium phosphate, sorry, over 1 mole of the barium, barium phosphate. Moles of the barium phosphate cancel out. I have grams of the barium phosphate. So now all I need to do is multiply across top, divide by what's on the bottom, and I'll get the grams of the barium phosphate that came from 300 milliliters of the barium nitrate reactant. So then if I calculate that out, I get 606.02 grams. So I get 6.02 grams of the barium phosphate. Okay, so 300 milliliters of the barium nitrate gives me 6.02 times 6.02 grams of barium phosphate, but I still have the other reactant, right? So they give me 100 mils of the 0.3 molar solution of sodium phosphate. So I have to calculate how many grams of the barium phosphate that will produce, assuming that it reacts completely. So I'm going to take the 100 mils. So I have 100 milliliters of the sodium phosphate over 1. And again, I'm going to do the same sort of conversions. I'm going to convert this to liters, then use the molarity to convert to moles, and so on. So first, same as here. So I'm going to convert milliliters to liters. So 1 milliliter, again, this is the solution. 1 milliliter of the sodium phosphate solution is equal to 1/1000th of a liter of the sodium phosphate solution. So milliliters of the sodium phosphate solution will cancel out. Now I have liters of the sodium phosphate solution, and so now I can use the molarity, 0.300 molar. That means that for every 1 liter of the solution, I get 0.300 moles of the sodium phosphate. So I'm going to put on the bottom liters. Since I have liters here, I'm going to put liters on the bottom. So 1 liter of the sodium phosphate solution, and on top 0.300 moles of the sodium phosphate. And so liters are going to cancel out. Now I have moles of the sodium phosphate. So then I'm going to use the mole ratio between sodium phosphate and barium phosphate. Here it's 2 to 1. So my next step is to put, I'm going to take the 2 moles of the sodium phosphate, put it on the bottom. And 1 mole of the barium phosphate on top. So moles of the sodium phosphate cancel out. Now I have moles of the barium phosphate. And again, I'm going to use the molar mass to convert to grams. So now, last step, same conversion, 1 mole of the barium phosphate on the bottom and 601.93 grams of the barium phosphate. Okay, and so now moles of the barium phosphate are going to cancel out. And again, all I need to do is multiply across top, divide by the bottom, and I'll get the number of grams. And when I do that, I get 9.02895, 9.029 grams of barium phosphate. Okay, so now what I've done is I've taken the 2 amounts, I've taken the amount of each reactant, and I calculated how many grams of the barium phosphate would be produced by each of those reactants, assuming that the reactant went to completion, like you used up all the reactant. All of that reactant was converted completely to product. And what you notice is that the 300 mils of the barium nitrate would only produce 6.02 grams of the barium phosphate, assuming it was all reacted, right? And the 100 milliliters of the sodium phosphate would produce 9.029 grams of the barium phosphate, assuming that it all reacted. Well, if the maximum amount of the barium phosphate that can be produced possible from 300 mils of barium nitrate is 6.02 grams, then that is the maximum you can get, right? You can't go beyond what this is able to give you. So even though you could possibly get this amount from this, you don't have enough of the barium nitrate to do that because this will only give you this amount. So that means that the barium nitrate is the limiting reagent, and this is the mass of our product. So that's the mass of our product, and this is the identity of our product, the white precipitate. Okay, so that's A. What about part B? What are the concentrations of all species still in solution? So this is going to take a little while, but we got a lot of work to do. So what I'm going to do is I'm going to erase this. I'll keep this information here, and we'll do part B. Okay, we're back to do part B. So part B here is, what are the concentrations of all species still in solution? So what are the species in solution? That what they mean there is, what are the ions that are in solution still? So we have a precipitate. So this precipitate involves barium ions and phosphate ions. We want to know how much, if any, of those ions are still in solution, and the sodium and nitrate ions that are still in solution. So the first thing we want to do is calculate the moles of all of the ions before and after, right? So we want to calculate the moles of barium ions, nitrate, sodium, and phosphate ions that were in solution before they reacted, and then what are the moles of ions involved in these products here. Um, so, well, with the sodium and the nitrate, those aren't reacting, so whatever we have here should be the same that we started with. So that's going to be pretty easy. Now for barium and phosphate, we'll have to figure out how many moles of the barium and phosphate ions that are in this product and compare that to the number of moles of ions that we started with. So here and here. So let's go ahead and start with the 300 mils. So we'll start with 300 mils. Let me make sure I get this right. It's going to be 300.0 mils. I forgot the zero up there. So it'll be 0 mils of the barium nitrate. And that's going to be NO32. And again, we're going to do the same conversion. So we're going to convert this to liters. So 1 milliliter of the barium nitrate solution. And then that's going to be equal to 1/1000th of a liter of the barium nitrate solution. And then we're going to use the molarity, 0.100, to convert to moles. So 1 liter of the barium nitrate solution on the bottom, and 0.100 moles of barium nitrate. So here, milliliters of the barium nitrate solution cancel out. Here, the liters of the barium nitrate solution cancel out. And then we have moles of barium nitrate. So if we calculate this out, we get 0.03. So we get 0.03, and then let's see how many sig figs we have. So we have 3 sig figs here, we have 4 here, so we should have 3 sig figs here. So, and I'll just put another one in there just to be on the safe side. So we have 3.03 moles of the barium nitrate. So barium nitrate. Okay, so this is the moles that we started off with the barium nitrate. Now we want to look at the ions themselves. So we look at the mole ratio. Here we can use the mole ratio from the formula itself to get the moles of the substance to moles of the ions themselves. So if we have 0.3 moles of the barium nitrate, If we convert this to moles of barium, it would be for every 1 mole of this formula, we get 1 mole of barium or 1 atom of barium. So the ratio is for every one of these, you get 1 of those. So it's a 1-to-1 mole ratio. So you have 1 mole of barium nitrate on the bottom and 1 mole of barium 2 plus ions on top. Moles of the barium nitrate cancel out, and we get the same molar amount, 3,000 moles of Ba2 plus ions. And then you do the same thing for the nitrate. So we'll start again with 0.03000. I put a 0 there. I'm only putting an extra digit to avoid rounding mistakes, but you don't need to do that. So there's moles of barium nitrate over 1. And then if we look at the mole ratio in our formula for the nitrate, so for every one of these, you get 2 nitrates. So it's a 1-to-2 mole ratio. So for every one of these, you get 2 nitrates. So I'm going to put 1 mole of barium nitrate on the bottom and 2 moles of the nitrate ion on top. The moles of barium nitrate cancel out, and you get double the amount. So this is going to be 0.06000 moles of the nitrate ion. Okay, so these are the mole amounts of the nitrate and the barium ions that we had to start with. Okay, now we just have to do the same thing with the sodium phosphate. So let's go ahead and do that. Okay, so now we have sodium phosphate to do. So I wrote here the molar amounts of both of these ions. This is the limiting reagent, so we'll keep that in mind. And I have the gram amount of the barium phosphate that was formed. So let's go ahead and figure out the amount of each of these ions in solution to start with. So we'll start with the 100 mils of our sodium phosphate solution, just like we did before. So we have 100.0 mils of the sodium phosphate, Na3PO4. So we have that. And so what we're going to do is we're going to convert that to liters again. So 1 milliliter, again, this is solution. We're talking about the solution. 1 milliliter of the sodium phosphate solution on the bottom, and 10 to the negative third liters of the sodium phosphate solution on top. So milliliters of the sodium phosphate solution cancels out. Now we have liters, so we can use the 0.300 molarity as a conversion factor again. So here, 1 liter of the sodium phosphate solution is going to give us 0.300 moles. 0.300 moles of the sodium phosphate. So liters of the sodium phosphate solution cancel out, and then we do the conversion. So then this is going to become, again, this is going to give us 0.03000 moles of the sodium phosphate. So sodium phosphate, Na3PO4. So once again, we have moles of the sodium phosphate that we began with. So we're going to convert this now to moles of the ions that we started with before the reaction. So again, I'm going to take the mole ratio from the formula and convert that to moles of each ion. So I have 0.300 moles of the Na3PO4. I'm going to convert that to moles of sodium. So you see here that for every one formula, you get 3 sodium. So that's a 1-to-3 ratio. So that means for 1 mole of Na3PO4, you get 3 moles of Na plus ions. So moles of the sodium phosphate cancel out, and then we get 0.9000 extra 0 just in case. And that's going to be moles of Na plus. Okay. And then we do the same thing with the phosphate. So we're going to start with 0.300 moles of the sodium phosphate over 1. And we see here the mole ratio is 1-to-1 for the phosphate. So for every one of these, you get 1 phosphate. So 1-to-1. So that means on the bottom, I'm going to put 1 mole of the sodium phosphate and 1 mole of the phosphate ion on top. So the moles of sodium phosphate cancel out. So it's 1-to-1. So this is going to give us 0.3000 moles of phosphate ion. And again, I'm just putting an extra 0 just to avoid rounding mistakes. But I mean, you don't really need it. Okay, so now I have the moles of the sodium, moles of the phosphate. So now our next thing is to figure out the moles of the barium and the phosphate that ended up in our precipitate, because those are no longer in solution. So we'll need to figure out the moles of these two and then subtract those from the numbers that we got here and here. So that would be the next thing to do. Okay, so now we're going to take the 6.02 grams of the barium phosphate, and we're going to convert that to moles. So we're going to use the molar mass here. So we used that before. So since we're using molar mass, grams is going to go on the bottom. So that was 601.93 grams of the barium phosphate. And on top is 1 mole of the barium phosphate. Grams of the barium phosphate will cancel out. And when I calculate this, I get 0.1000. Yeah, that's pretty much it. So that's going to be moles of barium phosphate. Okay, now that I have the moles of barium phosphate, I can convert this to moles of the barium ions and the phosphate ions that ended up in the precipitate. So let's go ahead and do that. So here I have 0.1000 moles of the barium phosphate. For the barium, it's a 3-to-1 ratio. So for every one formula unit, you get 3 atoms of barium. So it's 1-to-3. So we're going to use that as our mole ratio. So 1 mole of the barium phosphate on the bottom, and then 3 moles of barium 2 plus ions on top. So moles of barium phosphate cancel out, and so it becomes 3 times 0.1, so that's going to be equal to 0.300 moles of barium 2 plus ions. This is the number of moles that we're taking into the precipitate. These are no longer in solution. And then we do the same thing with the phosphate. So here we have, again, 0.1000 moles of the barium phosphate. And here you can see it's a 2-to-1 ratio. So for every one of these, I have 2 phosphates. So that's my mole ratio for phosphate and barium phosphate. So on the bottom, I'm going to put 1 mole of the barium phosphate. And on top, I'm going to put 2 moles of phosphate ion. So 1 mole, the moles of barium phosphate cancel out. I have 2 moles, 2 times 0.1. That's going to give me 0.2000 moles of phosphate ion. Okay, so these are the moles of the phosphate and the barium that ended up in the precipitate. And if we compare that, we'll be able to figure out the concentrations. But first, I have to make a correction here. Sorry, some of you probably picked up on this. I forgot a 0. So it's 0.01, which would make both of these 0.01 and 0.01, and which would make these 0.03 and 0.02. So just a simple mistake, but you don't want to make that mistake. So make sure you don't make calculator mistakes. Okay, now, so we have everything set up. It's important to keep in mind. So I'm going to outline these in a particular color so that way we remember. So these are no longer in solution. So this is the number of moles of barium and phosphate that are no longer in solution. And now that we have the moles of all the ions, we can calculate the concentration, because we can't lose sight of what they're asking. So they want to know, what are the concentrations? So the concentration is moles divided by liters of the solution. So keep in mind that we mix these two solutions together, so the volume has changed. So we mixed 300 milliliters with 100 milliliters, so that's a total of 400 milliliters. And so 400 milliliters, if we convert that, so 400 milliliters over 1 milliliter is equal to 10 to the negative 3 liters, or 1/1000th of a liter. So that's going to be equal to 0.400 liters of solution. So we now have the volume of our new solution with everything mixed together. So now we can calculate the concentrations. So let's start with sodium and nitrate. Those were not involved in the reaction. So whatever amount we started with before the reaction, that's the exact same amount we started with after the reaction. So the moles don't change. So we have 0.900 moles of sodium. So if we calculate the number, the concentration of that, let's erase this so we can give ourselves some room. Okay, so we're going to erase this because we don't need this anymore. Okay, so we have 0.900 moles of the sodium, Na plus, and we're going to divide that by the total volume, 0.400 liters. And when we calculate that, we get 0.225. So 0.225 molar Na plus. So this is the concentration of Na plus in our solution after the reaction. And we can do the same thing with nitrate. So nitrate stays the same. So we started with 0.600 moles. We still have 0.600 moles. So we're going to do the same thing. So we're going to take 0.0600 moles of nitrate ions. Divide that by 0.400 liters. And when we do the calculation, we get 0.150. So 0.150 molar of the nitrate ions. Okay, so we have the concentration of sodium and nitrate. Now we need to get the concentration of the other two. However, barium, some of the barium was taken up into the precipitate. So this amount we have to subtract from our original amount. What was our original amount? Our original amount was 0.0300 moles. That's what we started with. And the amount that ended up in our precipitate is the same amount, which means that all of our barium was incorporated or taken up into the precipitate, which means we have zero concentration of our sodium left. So the concentration of sodium is 0. So 0 molar of our barium. So no barium is left in solution. So 0 concentration. Last, we have our precipitate. We have our potassium ion. Potassium, what am I talking about? Our phosphate ion. And so here we started with 0.300 moles. And here we end up with 0.02 moles. So we have to subtract. But first, I have to correct a mistake I made. So I again forgot the extra 0 here. So again, our original concentration, our original calculation gave us 0.09, and here it was 0.03. Sorry about that. You guys probably caught it before I did. Okay, so 0.09 is the amount that we started with the sodium, and so this should be here 0.09 as well. But these are still the same. So these are the answers I get when you convert this. So this should be 0.09. That's correct. So this is still the right answer there. All right, so here we have 0.03, 0.03. So the barium is 0. And so for the phosphate, we started with 0.03 molar. And here we end up with, in our product, in our precipitate is 0.0200 moles. So we have to subtract that. So if we take 0.0300 moles of our original phosphate in solution, subtract the amount that went into the precipitate, 0.0200 moles, and then we get what's left over, 0.0100 moles of the phosphate that was originally in solution. So this is what we have left in solution in terms of moles. Now we just divide that by the volume. So 0.0100 moles of the phosphate over 0.400 liters. And when we calculate that, we get 0.025. Let me double check that. That is correct. So 0.0250 molar PO4 3-. So that, ladies and gentlemen, is the molarity of the ions that are left in solution after the reaction. Okay, so now we're done with part B. We found the concentrations of all species, of all ions in solution after the reaction, after the substances are mixed together. Now, for part C, where they want us to demonstrate that your answer to B is electrically neutral, meaning that all of the positive ions together equals the amount of negative charge. So all of the positive charge should be balanced with the negative charge in solution. Okay, so how do we do that? Okay, so let's look at the moles of the ions that are left in solution. So we're ignoring barium, right? So barium is not in solution. So what we need to do is calculate the total amount of negative charge, calculate the total amount of positive charge, and see if they're equal. Okay, so here, this is where are our moles? Okay, so here we'll go back to moles. We don't want to use molarity. We want to go back to moles. So here we have moles of our phosphate left over. So this is the moles of the phosphate left over. So we have 0.0100 moles of the phosphate, and all of those have a 3- charge. So we're going to have to multiply this by 3 to get negative charge from the phosphate. So let me go ahead and clean this up a little bit. Okay, so now that I got everything kind of organized here, so this is what we have left in solution for each of the ions. So we have 0.0900 moles of sodium. Each sodium ion has a +1 charge. So that means that from the sodium, we have 0.0900 moles of plus charge. You can think of it that way. So we have sodium in solution. So this is the amount of sodium we have in solution. So we have 0.0600 moles of the, did I say sodium? I meant nitrate. So nitrate in solution, each nitrate has a -1. So that means that we're going to have 0.0600 moles of negative charge from the nitrate. And then we have our phosphate ion that has a 3 negative charge, and we have 0.0100 moles of that. But since each phosphate has a 3 minus charge, we're going to have to multiply this by 3. So 0.0100 times 3 is 0.0300 moles of negative charge. Since these are both negative, we can add those together. And add those together, we get 0.0900 moles of negatively charged from our ions. And so we can see here that this amount of positive charge is equal to this amount of negative charge. So that is the answer. That's how you can show that this is electrically neutral. I hope this is helpful. I know this is a long video. There was a lot to cover, but I hope you learned from it. I hope you found it entertaining and helpful. If you did, then please like and share the video. Hit that like button somewhere around here. Help me out with the channel by subscribing to the channel. Hit that notification bell. When you do, make sure that you click all so you can see all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem you want me to cover, if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.